In this video, we are going to talk about hydroboration oxidation reaction of alkenes and alkynes, and also stereochemistry in hydroboration oxidation reaction. Now let's consider this molecule. If we pass this molecule through borane in the presence of tetrahydrofuran, that is the hydroboration part, and then in the oxidation part, we pass it through hydrogen peroxide in the presence of sodium hydroxide and then water. What will be the product form? Now, hydroboration oxidation reaction is a syn addition, and also it is an anti-Markovnikov addition. So since it is an anti-Markovnikov addition, it means that you are going to form a molecule where the proton will go to the more substituted side. So the proton comes here. So here is a proton, and then an OH going to the less substituted side. So there's also an OH group here. Now, it is a syn addition, and therefore there is stereochemistry in this reaction. How does this reaction happen? Let's consider boron. Boron it has atomic number of 5. Let's write down its electron configuration. That is 1s2, 2s2, and then 2p1. Now you can see that these 2s2 and 2p1 will form the valence electrons of boron. So in terms of hybridization, then boron is going to mix 1s orbital with 2 of the p orbitals. So let me show it here. So let's say this is 2s orbital, then 2px, and then 2py orbital. Then the 2pz orbital is here. So if we hybridize this, since there are 3 electrons, then according to Hund's rule, there will be a single filling. Now, if we take BH3, there are 3 protons, and each proton has a single electron. So the protons will pair up to form this octet, and then an empty orbital. Now, this empty orbital in boron is the driving force behind hydroboration oxidation reaction. So it is this empty orbital that enables boron to accept pair of electrons from nucleophiles. So having understood the structure of boron, let's go ahead and do the mechanism. So let's consider the alkene. You see that the alkene has pi electrons, and therefore that makes it a nucleophile. But boron has empty orbital. So what will happen is that the alkene will move its pair of electrons into the orbitals, the empty orbital of boron. At the same time, boron will become destabilized. Boron will always want to have 3 bonds. So therefore, because there is a 4th bond forming, it will force boron to throw off one of its hydrides. So it is more or less an SN2 reaction, and that will lead us into this intermediate. So this is the intermediate that we will get. However, we have said that this reaction is an anti-Markovnikov reaction. And why is it an anti-Markovnikov reaction? So let's consider these 2 intermediates. You see that if the boron, the electron pair were donated from this carbon onto the boron, then the primary carbon will bear the positive charge, that is positive formal charge. But if they were donated by this terminal carbon, then it is this carbon that will bear the positive formal charge. However, you can see that this is a secondary carbocation, and this is a primary carbocation. A secondary carbocation is more stable than a primary carbocation, and that is why this reaction proceeds through the anti-Markovnikov addition. Now, having gotten this, there is a lot of the 1 propene in reaction in the solution. So therefore, in the next step, this would donate, sorry, this would donate pair of electrons to the boron, and then the boron would move this hydride to this place. So this will cause this intermediate to form. Now you see that there is also another proton here. So there is more 1 propene in solution. So another 1 propene will attack the boron. Okay, so let me draw it like this. So this one will attack this boron again, causing the boron to move its hydride molecule to this place. And therefore, this will be the intermediate that will be formed. So this is the molecule that we will get after we are done with the hydroboration. Now let's come to the oxidation step. In the oxidation step, remember that there is hydrogen peroxide in solution, and there is also sodium hydroxide. So this OH would pick a proton from the hydrogen peroxide, and that will force these electrons to be moved on to this oxygen. So we are going to get this molecule in solution. Now, you can see that this is a nucleophile, and therefore it can donate its electrons to the empty orbital of boron. So what will happen is that this will donate electrons into the empty orbitals of boron to form this intermediate. When this intermediate is formed, it will give boron a negative formal charge. So this negative formal charge will make boron unstable, and therefore it will force boron to move one of its alkyl groups to attack this proton, to attack this oxygen. Now oxygen-oxygen bonds are so unstable, and therefore it will cause this OH minus to leave. So in the next step, we are going to form. So this is the molecule that we are going to form. Now this step will keep repeating itself for 3 times till all the oxygens are sandwiched between the alkyl groups and the boron. So this is the molecule that will be formed in solution. So remember that we had OH minus in solution because we threw off OH minus in this step. So that OH minus is a nucleophile, so it will donate its lone pairs into the empty orbital of boron to give this molecule. Boron is unstable with 4 bonds. It will cause one of the alkyl groups to cleave, and when it cleaves, it will bring us into this step where we have this molecule, and then the other boron. Remember that there is water in the system, so this nucleophile will pick a proton, creating a hydroxide in solution. So this will lead us finally into our product, which is this product, then plus OH minus in solution. So this is the mechanism for hydroboration oxidation reaction in alkenes. If we put it in a bulky alkyl in the presence of tetrahydrofuran, and then hydrogen peroxide in sodium hydroxide aqueous and in water. Then this reaction is also going to follow the anti-Markovnikov process, and it is also a syn addition. So we are going to form an alkenol. This is the molecule that we are going to form. And this molecule will tautomerize to give us an aldehyde. Now, what is the mechanism for this reaction? Remember that in this case, we didn't use boron. However, we use diphenylboron. And this is because if we use boron, both pi bonds of the alkyne will be substituted. And therefore, we are using a more bulky boron. So what will happen is this. So we have and then the phenyl groups here. So it will use one of these pi bonds to attack boron. And then boron will give off a hydride to give this intermediate. Remember that there is hydrogen peroxide in the solution, just as it happened in the alkenes. So this one we use to attack the boron to give us this molecule, to give us this intermediate. Now, remember that boron does not like forming four bonds, so it will cause this to move here, whilst causing OH to go away. So it will lead us into this intermediate. So this is the intermediate that is going to form, and it will force boron to cleave off this, so that at the end of the day, it will lead us to this final product, alkenol. However, this alkenol is not stable in this form, so it will tautomerize. Let me show the tautomerization in this place. Remember that this is an OH, and then there is an alkene. So this is a nucleophile. So because of the electronegativity difference between oxygen and hydrogen, then oxygen has a partial positive charge, and hydrogen has a partial positive charge, and the oxygen has a partial negative charge. So this nucleophile will attack this proton, forcing this bond to move into this carbonyl center. So that will give us our final product, which is this. With final product will tautomerize itself into an aldehyde or a ketone, into an aldehyde. So this is the procedure by which hydroboration oxidation reaction happens in alkynes. Determine the final product of the following reactions, which is this molecule undergoing hydroboration oxidation reaction. Now, because it is a syn addition, then we are going to produce a molecule in which both the OH and then the proton is on the same side. However, the attack will happen on either side of the molecule, and therefore you produce both the cis and then the trans isomers of this molecule. So this is the product that is going to be formed. So reference to this molecule, remember it is an anti-Markovnikov addition, This carbon is more substituted than this one. So the proton will go here and then the OH will come here. So these are the products we will get. And then here will be a wedge bond. So these are the two possible products that can form. And then in this case, and then the hydrogen goes here. And let's come to this one. See that we can form this molecule. Where the proton is here and then the OH is there. And when we come to this molecule, see that, sorry, this side is more substituted than this side. And therefore, the proton goes here. And then the OH comes here. Or so I need to pin this. This is the proton. And then this is the OH. So these are the possibilities of molecules that we can form.